Hello and a very warm welcome to our second week of a little series of online seminars on measuring and testing of networks and cables here at Softing IT Networks. My name is Alfred Huber and I will take you to this presentation today. And as usually, I'm not alone here to do this. I have as we call it, a co-pilot who wants to introduce himself and his role today again. And yeah, Alex.
Hello, welcome, a warm welcome also from my side. My name is Alexander Boy and I'm product manager in the house and responsible for a lot of our testers. You have today on your screen a control panel where you see some interesting parts, for example, questions in a chat window. When you have any questions in between of our webinar, you can write some questions and I will answer to you, or on the end of our webinar, we do that together. Then we have handouts prepared for you. Now in the meeting, you can download all the attachments, what is available for you to see that later again. So have fun with our webinar today and see you later.
Alex, thank you very much for the introduction and for the little housekeeping. So what's the topic today? The topic as promised last week. Last week we had the basics on coppers. Today we want to dig a little bit deeper into this and I called it the advanced part of that. And let's have a brief look to the agenda of this presentation. So first of all, to the people who are new on these series of webinars, a little introduction to Softing, who is Softing. Then we make also a 5 minutes repeating of the last week, what is testing, what is measuring, the verifying, qualifying, certifying, talking a little bit deeper into standards, because standards are very important today. And then for about half an hour, 40 minutes, we will dig very deep into the topic of certification of a network link. I call it the King's class of the measurement. And all the related stuff like link definitions and the parameters we are testing. So that will be the main topic of today. And finally, we look very briefly to the instrument who is doing all this nice job, to talking a little bit about the wire expert. Okay, that's the agenda of the day. So let's start with the introduction of Softing. Softing is a mid-sized German company based in Haar near Munich, nearby Munich. Here we are about 400 employees, founded the company in 79, went public in 2000. We have local representations all over the world. So very nice mid-sized company. So the company's business sits on 3 columns, as you can see over there. So the columns are automotive, IT networks, and industrial automation, to be precise. So what are these colleagues doing? The automotive guys are testing control units, EPUs of cars, and delivering software to this, and a lot of testing surrounding the environment of automotive. Industrial automation, these guys are helping people to set up production lines and delivering gateways to allow communication between different field bus languages. They're also gathering data to analyze machine data, so which is very important for preactive maintenance of machines and so on. We in the middle, we are the youngest child in the company. So IT Networks is basically doing test and measurement instruments for Ethernet cabling, let's say this way, and we coming from the office environment. But in the meantime, there is a strong tendency of Ethernet going also into other areas of application, and strong areas going into is the industrial environment over there. There's a slogan called Ethernet goes industry, and Ethernet is starting to replace starting is not a word, is in the mid of replacing all the field bus systems we have currently in this production area, is going to be replace everything with Ethernet. Similar things are happening to the automotive area. Automotive, we know car is controlled by a CAN bus. CAN bus is a very slow control bus, so it's too slow actually to be used for autonomous driving, for example. So a modern car who offers you all these nice support tools to have kind of an autonomous driving are controlled by another bus system, by an Ethernet bus. 10 gigabit Ethernet is very popular now in an automotive, in a car, for example. So, and every place where Ethernet is moving in, it needs separate testing of the cabling. The Ethernet protocol relies on a working transmission line. And we have to make sure that these transmission lines are properly working, and we do it through our test and measurement equipment in all areas where Ethernet ends up at the day. So, of course, we are focused today on IT networks. That's where we are working for. Where are we located? Here, a quick view on our worldwide offices. So the headquarters is here in Munich. We have a very strong branch down in America, in Knoxville, supporting the whole Americas. We have also a very strong branch down in Asia, in Singapore, where these high-end test instruments are designed. We have a couple of sales outlets spread over Europe and the world, let's say. So a few names, a few cities: Lyon, Barcelona, Vienna, Milan, and of course the big Chinese market in Shanghai. We have one office. Okay, so let's dig into our topic of today and do a quick repeating of our instruments we offer. Call it the commercial slide. So these are the instruments. Let me just open all the slides. These are the instruments we are selling to the market, and we group them into three major groups. One is start from the low end, is verifying, low-end tester, testing the wire map, for example, on copper. Then we have qualifiers, very strong group of testers nowadays, testing a transmission link with an application, looking for errors, looking for lost frames, so on. And also the top range of measurements. It's a differentiation of testing. So the measurement instrument for copper and for fiber, Wire Expert and Fiber Expert are the names on this. Okay, but let's quickly move on and go directly to our topic. Test and measure and the three definitions of test and measure. Basically, let's start again with our challenge. For example, this is a company. The company is spread through 3 buildings on a certain campus, local area called. So we're looking for local area networks. So the first job is to connect all these 3 buildings together to allow communication between the buildings. So we have these primary levels, it's called. The primary level is done by fiber optic cabling. This is typically the area of single mode cabling. By the way, we are talking about fiber optic testing in depth tomorrow. Just a little hint already. We are going into the building, so we have to connect the different floors together, secondary level. So this is done, of course, again with fiber optics for various reasons, topic of tomorrow. Then we turn to the floor, to the individual floors. This third area, and this is usually done in copper. Copper is extremely strong on this area. We hear later maybe why it is. And we have a fourth technology in the building. Let's say this is Wi-Fi. Nowadays, every network is containing some Wi-Fi components, but this is not the topic of today. Today, we stay here on this level here, on the copper level, and want to dig very deep into testing and measurement of these things. So what is test and measurement as a group? So as we started, as explained already last week, so the start off of testing is verification. Verification is just testing proper wiring of a network. That's the job. Full stop. Okay, then in older days, we went immediately to certification. Certification is now the opposite of very basic testing. Is absolutely detailed testing of a lot of low frequency and high frequency parameters, and summing up 14, 15 parameters. And when all parameters of the measurement are okay, it's allowing us a statement, this link will definitely work up to a certain frequency. Okay, this is certification, and this is what we're talking today about in very deep detail. There's also a big jump between the pricing of these test and measurement instruments, between verification starting at 60 euros and certification starting about 6,000 to 7,000 euros. And to bridge this gap, there was invented qualification over the years. And qualification is also testing a transmission link, but it's just testing, means it takes the application, it takes an Ethernet protocol, and it's sending data basically, and it's trying to find out, is any data lost over time? And if the data is not lost over time, it allows us a statement, this link is good, for example, for 1 gigabit Ethernet transmission, for 10 gigabit Ethernet transmission, and so on. Okay, that's qualification. And on the first point, we added active and troubleshooting testing to this lower groups of testers, to the verification and the qualification. They can also help you to start up a network, to do the active basic testing, checking for some address system and doing some ping, looking for stations in the network. So it helps you on activating a network. And it's also helping you on troubleshooting if something is not working properly, you can't address a certain terminal instrument and so on. So this is features which are added to the instrumentation, verification, and qualification. I think you can hear more about this active stuff on Thursday this week, where we talk about exclusively on this, on the basics of this active testing. Okay, but today we want to dig into certification, which is the classic acceptance measurement for a network. And it's basing its information or its its values results on a certain number of measurements it's doing. And if the measurements all are passing, it allows to give a statement, this link will be good enough for a certain class. It provides a certain bandwidth, and this bandwidth allows you to run a certain application over this transmission link. The limits it's looking at are based on standards. We will see in a minute about what standards are there out in the market, and we have to take care on this, and you have to comply to this. And also a topic was very interesting is about link definition. What are we actually going to measure on these systems on a transmission link? Do we include the patch cords? Do we leave the patch cords out? So is the system always built on the same components, an outlet here, an outlet there, a cable between? Is there any breaks allowed between the cables, and so on? So this is what we are going to talk about today. So let's start with the basics. Let's start with the standards. So this is a big list of standards. I compiled this list once to give the people a little glance of this world we are living in, and the world we are living in is completely standardized. Though there are existing standards just for the cables, there are standards for the components we terminate to the cables. And how to do this? How to do this properly? There are also standards to teach us how to do this properly. So this standard is telling us how to properly connect components to a cable to make sure it's working properly. Plus, of course, the instructions of the manufacturer of the components. And if these components, standardized cable and standardized components, are properly installed, what we get is a working cabling system. And this cabling system also gets its own standardization. And to check whether the cabling is matching these limits, this is what we are doing when we do a certification run. Okay, so today we are talking about certification. We are checking against cabling standards. And you see there are certain standards on the world. There is the American world, the tire world, the ANSI tire world with their own standards. And we have the international worldwide standard, the ISO, International Organization of Standardization. And we have, based on these international standards, the European standards. And there's even a lower level beyond these European standards is the local standards in local languages. So for Germany, we have the DIN standards, Deutsche Industrienormung, which is the same standard as the European one, just translated into German language to be easier used. Okay, and to make sure that the measurements are properly done on a cabling system, we also have standards which explain or tell us how to do the measurements and against what standards the instrument have to be compared and what accuracy level they have to compare. So this is, in a very quick look, this is the overview on the world of standards we are working in. And we have to make sure that we only use, when we do a proper installation, proper material, cable which meets standards, components which meet standards, and the measurement has to be standardized as well. So that's the world we are working in. So if we have a little look now closer to this green sector here, to the cabling, how is the cabling standard structured? Let's have a quick look to this. So I open now up this green column. So what you see is again the American standards, ANSI tire 568. We have the international standard. The Bible of networking is ISO 11801-1. Now it's in its third edition. That's not an official name, but it's the inside name. And derived from these international standards, we have the European standards, the CENELEC standards. That's the standardization group, the CENELEC, and it's called EN 5173-1. Okay, excuse me. And now we are grouping the individual performance levels of a transmission link into these groups here, into these different bandwidth requirements. So we have a bandwidth requirement that goes up to 100 megahertz. This 100 megahertz is called a Class D network. Let's do a jump. Let's go to 500 megahertz. 500 megahertz is going up and called a Class EA. You see the difference between the international and the European standards to the American ones. The American ones call this standard category 6A. They call this standard category 5A. So it's very easy to recognize an American standard in a test instrument because you're just getting offered this category and plus a number. So usually here in our area, Europe, we don't use American standards. We are using international standards or the European standard, which is derived from the international one. So this gray field in the background tells us that the values in an international standard and in the European standard are exactly the same. So the same limits. It's just a different, let's say, a different cover sheet on the standard, but the values, the limits are definitely the same. So it doesn't make a difference in doing an actual measurement against a Class FA standard, EA taken out of the ISO or taken out of the Senelec of the EN standard. That's very important. So we have it in the measurement instruments. All manufacturers have it multiple times in the instruments just to provide the proper statement on the test report. So the planner wants to see, oh, this has to be tested against the ISO, so we can make it look on the certificate. Here is the ISO, the reference. Okay, so 500 megahertz, where I stopped, and if you go on, you see at the very end, you see here the Americans have a gap in between, so they never took care about 600 and 1000 megahertz. The 600 and 1000 megahertz bandwidth is an international thing, let's say, and it's based on non-RJ45 connectors. As we saw last week, there are connectors like the Terra, the GG45, or the EC7, or the MMC Pro is called nowadays. So these connectors are different, completely looking different as the RJ45. They have far better performance in NEXT as the RJ45, but they never really made it into the wide area, let's say, into the field, because they are very expensive and they're not RJ45 compatible. And I think the active manufacturers, the active component manufacturers, like switch manufacturers, never jumped on the train of a different interface as the RJ45. So it's a very small niche products, these products 600 and 1000 megahertz. But where we are again back on the track is 2000 megahertz, 2000 megahertz on RJ45. It has less headroom on NEXT, for example, as these two here, but it's working. It's working up to 40 gigabits on a shorter link transmission line. So we're here down to 30 meters, not to the typical 90 meters or 100 meters as we are. But this is existing category 8, and the category 8 is in the ISO as well, represented as class, the Roman 1 and the Roman 2. And the same works in the Senelec in the European standards. So just to make sure that we are setting up the proper standards, I always recommend to installers here in our Europe, just look for a class in the instrument plus a letter behind it. Then you're always on the right track. You just have to match now the letter to the requirement of the customer or of the system which the system is offering to you. Okay, so here in our areas in Europe, we are testing against classes, not against categories. Okay, let's spend one other slide on category and classes. What's the difference between category and classes? We also in our area use the word category, but we use it here just to define the bandwidth of a component. Component means cable and excuse me, cable and component, which we terminated this. Okay, and these categories and the number are matching here to the bandwidth we offer. Okay, so the American do the same without the 600 and 1000 megahertz. But now when it comes to a link, which is comprising minimum out of 2 components and a cable in between, we are switching here in our area completely to a class definition. So when we want to find out how good a link is, we always set up the instrument to measure against a class. Okay, the Americans keep the categories and do measurements against categories. So make sure always when doing measurements in our area, go to the class definitions and watch out for the proper matching with this bandwidth. Okay, and also make sure when doing testing that the instrument doing the testing has the proper accuracy level, because the accuracy levels are always matched to the bandwidth here the bandwidth groups we have here. Okay. You have seen this slide already last week. This is the matrix of applications matching to the bandwidth here in the various standards, in the classes, in the categories. I just wanted to point out, okay, you have seen this already. So when we go for 10 gigabit Ethernet, it's good enough to have 500 megahertz bandwidth. If we only do one gigabit, it's good enough to have 100 megahertz network. So there is no direct relation between the number of megabits and the number of bandwidth in megahertz, because the coding and the modulation is let's say, to compress this data information, to squeeze it into a smaller bandwidth number as the megabits or gigabit number is telling you. Okay. So now let's go into certification. Let's jump into the King's class. And as I said earlier, first of all, we have to define what do we want to measure? What part of the installation do we want to measure? And there's a simple statement. The target we want to measure is the so-called permanent link. What is permanent link? Permanent link is defined as the, let's say, fixed mount part of the network. It starts usually at the cabinet and it ends at the outlet in the room. That's typically the permanent link. And permanent link, as you can see here, is measured between these blue dotted lines. So what's included in the permanent link measurement? Included in the permanent link measurement is definitely the connector from the test code. So the measurement has to start before the connector of the test code and ends in the same place on the other side. Okay, so that's important. What's not part of the measurement, what should not be part of the measurement, is this part of the measuring cable plus any adaptation here to the instruments. So the permanent link sits between the two ends here, including the connector of the test code. Okay. Unfortunately, there are now a couple of definitions of permanent link, and a couple of definitions has to do where this permanent link is used for. It's always the same piece of cable. Let's say it's a cable with two jacks on the sides. Okay, but we have a different usage of this. If you use this permanent link for a backbone, it's what's called in the older days. The older standard was called the usage PL1, permanent link in application 1. If you use the same permanent link as the connection between the floor distributor and the outlet in the room, it's called permanent link PL2. It's usage number 2. It's used as horizontal cabling, which was very nice to remember. So, okay, I'm measuring PL2, the cable with 2 jacks on the end. Okay, unfortunately, all this naming has changed. The standards have changed completely on this. ISO makes it, in my opinion, a little bit easier. They are calling now this kind of permanent link, they call it a 2-connection link, as we do it in the measurement instrument. Here above, you see the representation in our instrument. Okay, this is a 2-connection link. Unfortunately, the European standards have done something completely different. They gave these now letters. And so to use it as a backbone is called now, in EN, is configuration A. The same story to have it used as the typical connection between the distributor and the outlet is configuration B. Okay, now let's have a look to these other 2 here. Now we're looking to configuration C, or a 3-connection permanent link. What's the difference here? The difference here is this one here, the consolidation point. So, you know, consolidation point sits in the room where the outlet will be end up, and is a distributor, a passive distributor sitting somewhere on the floor, in the wall, or in the ceiling. And all the cabling coming from the floor distributor are ending up at this consolidation point. And from the consolidation point to the actual outlet where the computer is connected, there is interestingly a flexible cable used. So not this fixed cable as we use for installation, but here we have a piece of flexible cable ending up in a jack, starting in a plug. And this type of cabling here is called now a 3-connection link. The advantage why it was invented on the consolidation point is to be more flexible when the room layout is changing, when the desks are moved. So you can bring directly from the consolidation point to the individual desk, you can bring your signals and you can move the cable, the flex cable, to the desk, and you don't have things lying around on the floor and being dangerous on the floor. Okay, So if you want to do now a measurement of this system here, combined the fixed cable and the flexible cable, this 3-connection permanent link configuration C, you are allowed to use a different set of standards, which are a little bit lighter, a little bit softer as the hard standards we're using here. But you're not allowed to use that set of limits against a 2-connection link. So you see the difference you offer here in the instrument. So be careful. There's only a set of limits using for a 3-connection link and should only be used on a 3-connection link. If you don't have the last piece of this line available here, the yellow one, the flexible one, you can also measure just to the consolidation point. And if you do this, now we got ending up at configuration C, which is called the CP link, or also a 2-connection link. Okay, and interestingly, this has the same limits as the first usages of this cabling. Okay, there's permanent link. Just set up the instrument to the proper standard, the proper topology you want to measure, and make sure that you use the proper adapters here, permanent link adapters, so the instrument will automatically begin the measurement here and the measurement on the other blue line. Okay, that's permanent link testing. That's a typical acceptance measurement. What's not an acceptance measurement is to do a channel link measurement. The channel link measurement, you're not using the proper test codes, test reference codes. You are just using the patch code, which will connect later on this side, the network with the active switch. On the other side, you are already putting in the patch code, which is connecting to the actual computer, let's say, on the other side. And now you do a measurement starting from this point here, down the line to this point here. So you're ending up the measurements before the plug check combination on the test module of the instrument is. So what's not included in the channel link measurement is the first and the last connector of the whole link. Okay, that's important. Keep it in mind. We need it for the next topology we're going to measure. This topology is basically used for doing troubleshooting. If a passive link, a complete one, has already worked once and it doesn't work anymore, so try to find out why. First do a measurement of this passive channel link, and then you can dig into the details of the link itself. Okay, there are also various things allowed here, like cross connects and so on, and also consolidation point again. But there's only one set of limits, because it's only one set of limits starting here and ending on the other side. Okay, whatever is in between on passive material, this measurement doesn't take care about this. Okay, why I'm so keen on telling you that the measurements ending here and do not include that connector and do not include the last connector, because there's a new topology now in the market, let's say, and this is utilizing a different system. It's called the MPTL, modular plug terminated link. What does it mean and where it stands for? Modular plug terminated links are links which starting just normal here on the floor distributor with a typical jack. Okay, but what's on the other side? On the other side, on the end of the link, there is no jack here. There is a plug. This is a field mountable plug. You can mount on a fixed cable. Okay, so it's not this typical low-cost crimping RJ45 you use for Cat5 patch cords. It's really high-end plug with bandwidth up to 500 megahertz most of the time. Okay, why do we have here a plug and not a jack? Because this ends up, or this link is used a lot of times for fixed remote units, for fixed terminal units like access points, cameras, or what's very popular now is lighting. Okay, and there is no need on this side to have a jack and to have a patch cord going into the access point. So you directly try to connect here straight into this instrument on the far end side. Okay, now how to measure this? So looks easy. Okay, this side is easy. It's just a permanent link measurement as we did before to make sure it starts here. On this side, we have an RJ45 plug here now on this cabling. Usually we could use now our channel link adapter as we used before, where this plug fits very nicely in. The problem is only when we use a channel link adapter here, the measurement, the point of measurement is here. This is the reference plane of the measurement. So what's not included into the measurement is my field mounted plug here. But it's a very, very important part of the link. It's done by the installer itself, so it has to be in the measurement. So we have to find a way to shift the reference plane from a channel link adapter to here to include this connector and jack combination. And we already have modules on the market for every tester nowadays, which are providing this reference plane at this point, and they are used typically for testing patch cords. So definitely we have to use here to make sure to do a proper measurement, a patch cord adapter, or if you use a single one, it's called now the MPTL adapter. And these adapters make sure that the reference plane is here. So this is a valid and proper measurement of an MPTL link, okay? Not using any other adapters or combinations of channel and whatever supporting cables and various things which has been used in the past. So this is now specialized and standardized how to do proper MPTL measurements. Okay, let's have a look across the wall, let's say above the wall, to some other environment where now cabling is used. And this definition of a cable link is coming from the industry typically, and it's called end-to-end link. So typically this cabling is used to connect machinery in production areas. And they don't work anymore with data outlets, with jacks, and with patch cords. So machines are usually typically connected by one direct fixed cable plus two field mountable plugs on this side. Okay, so it's be very careful. It's a kind of a very long, high quality patch cord, but it's solid cable and it has proper high performance connectors on this side and the other side as well. Okay, so what's different now to the classical building constructions that we have? Different is definitely that we are using here our own set of measurement adapters. And we have to make sure that we start the measurement here, as we have seen on the MPTL. We have to include these plugs here definitely into the measurement. So if we would use channel link adapters, we would just ignore this. The same thing on the other side, just ignore that connector here. So we have to make sure to use proper, as we call it, industrial testing adapters. What's also different is it's not only RJ45. As we know from the office and the building situation, building environment, we are always using RJ45. Okay, in industrial environments, there are a couple of other different connectors which are used. Very typical ones are the M12 series, M12 with different coding, decoding, X-coding, IX connectors. There are a variety of different connectors. And we have to make sure that we have always the proper reference part on this side to do a proper measurement. So our system here at Softing allows us to swap the reference part of the measurement connector here, and then we can adapt to any different, every different type of connectors in the industrial environment. What's also different is that this cabling can be built up in certain parts. So so it doesn't have to be like in the office building, one cable through. We can allow up to 5 connections in an office in an industrial environment. So the reason why this is because in industrial environment, sometimes you have to connect to a machinery, and the machinery is encapsulated. And to make sure that you are moving properly between the different layers of the encapsulation, you have to open up or break the test cord. You can't simply drill a hole through all the encapsulations and put your cable in. You have to make a proper back-to-back connector in the different walls of the encapsulation and so on. And this leads up to this kind of topology, which allows up to 5 connectors in one of these cables. And this also has, as a consequence, different sets of limits in the standards. Okay, all these standards are programmed into the instrument, the end-to-end. So if you get in touch with industrial environment, you are already prepared. The wire expert is prepared. First of all, with the adapters, the proper ones to use, and with the standards in the instrument itself. Okay, now we talked about these link definitions, what we want to test. So we want to test basically in the office environment, we want to test permanent link. But what do we want to test? So let's have a look to the actual testing parameters. And if you look to the testing parameters, we can group them. We can group them into 3 different levels here. We can group them into low frequency parameters, high frequency parameters, and calculated parameters based on measured parameters earlier. And if we look to the individual parameter again and try to group it and to combine it with the component where these parameters are derived from or coming from or are influenced by, so we get this matrix as you can see here. So let's start with the first one. The first one is a very low frequency parameter, is testing the wire map with DC signals. And if something goes wrong, or who is reliable for the wire map, it's installation quality. So the installer, there is no automatically connecting outlet so far. So the installer is in charge when the wire map is wrong. Okay, if we go to other parameters like, for example, length. Length has nothing to do with the component. Length is simply a parameter of the cable used. Okay, but length is not directly measured, as we will see later. Length is also calculated from another measurement. Okay, we have the same thing for crosstalk, let's say. Crosstalk is nowadays more or less coming only from the components or from the way the installer has terminated the cable in the component itself. So this is the matrix you can do on testing. And this is the matrix of parameters you have to test. And there's also an optional group of parameters which either needs to be tested when referencing, when developing a cable or a component, or at a certain level, some parameters which are already included in test instruments nowadays can be used for field testing as well. And a very popular one is this DC resistance unbalance we will talk about in a minute. Okay, so now let's dig into the parameters. Let's start with the basic one. As we learned last week, the basic one is always wire map. Every instrument, every test and measurement instrument is starting with a wire map. We have these two wire map schemes, as we learned last week. We have the A scheme and the B scheme. What's trouble on both of these schemes? It's always this backwards compatibility to analog telephone system, which is giving us this funny construction here. Okay, we will see later when we talk about the crosstalk where the problem is coming from. Okay, so basically we started with wire map, and we can have these two different kinds of wire map, the A and the B scheme. How is the instrument talking to me about this? So here is the different schemes. Here is the A scheme, where the green one is on 1 and 2, and the orange one is on 3 and 6. 4, 5, the blue one is always the same, and 7, 8, the brown one is also the same pair. Okay, now the same in B, wiring diagram B. So you see a swap between the orange one and the green one. What's better? Nothing. So it's the quality is the same, the performance is the same. Just historically in the standard, and since this historic is our standards, we have to make sure that both ways are valid. Okay, so if everything is fine, we do the measurement here. So we got here very nicely a working wire map. If the wire map is working fine, the wire expert is continuing to do the measurements, and the overall result of the whole measurement now was a pass. You see this on the green tick here, and it's showing me the first two lines the least the worst, let's say the worst values for some certain RF parameters. And you can also access the locator from here where you find faults. We see later on. If the wire map is not right, the instrument stops at the wire map measurement, and here we see a few samples of wire map faults. Here you got the situation of open cables. Here you got the situation of shorted cables. You get an indication where the location of the fault is. As we have two similar instruments, two identical instruments, you get an information from each side you're looking into the cable. So if it's on one end, the one instrument will say it's at my end 0 meters, and the other instrument will say it's on the opposite end, maybe 50 meters or something like that. So this is sensitive to the instrument which is looking into the cabling. We have other wire map errors. We have here crossed pair, 7, 8 is crossed. We have here a very common fault. It's an A-B mixture, though this is the wire map how it's looking like when the A scheme meets a B scheme on the other side. Not very nicely. Here you got the most critical fault is split pairs, where the installer has opened up the pair system. So, and the signals are not walking through the cables on its defined pair, but they are just split it up in two different pairs. That's a very tough error on the RF side, and we will see later when we talk about the next error. This is one of the results. Next will definitely fail on this. Okay, this is a typical screens for basic wire map errors. Honestly, wire map errors are making about 80–90% of all errors you have in the field. So because this is the factor human being which is working on this. So let's go on to move on to the next parameter. Next parameter is DC loop resistance. It's mandatory in our standards. It's an optional parameter in the tire standards. Okay, loop resistance for all four pairs we are measuring against the limit given from the standard. And we have to make sure that all four pairs are below this limit given in the standard. If you do a very simple measurement of a system which is not related to high power PoE, where you know this is just an office communication, there's no PoE or very low PoE just involved, this DC loop resistance is good enough for a statement about low frequency DC resistance values. Okay, if you know that you're going to test a link which has to be used or will be used later on for high power PoE means above 50 watts, then this loop resistance measurement, this DC measurement, is not sufficient. You have to extend the measurement to this DC resistant unbalanced measurements. Then we're not stopping at the loop resistance measurement, very above. Then we have to also measure the difference in resistance between the individual pairs. Why do we have these differences in the individual pairs? Because the twist is different in the pairs, so the DC resistance is also different. And it goes even down, even deeper down. So we are going into the individual pair, and now we are also testing or measuring the resistance of each individual wire in a pair. And there's also a limitation about the difference here, the allowed difference between the resistances of the individual wires here. Okay, all this testing is to ensure that high power PoE will work properly on this transmission line. Okay, just make sure that you're using this measurement when you're aware that high power PoE is involved. It's not necessary on low power PoE, the first two standards on PoE, AT and AF standard. But if you're sure that the installation will be used for a BT installation on PoE, it's the standards wordings. So make sure that the instrument is also certifying DC resistance unbalance. DC resistance unbalance will extend the DC function on the instrument, and you don't have just only the loop resistance. Now we have the resistance between the pairs and the resistance differences within the pair. And this gives you a complete new block on the certificate you see up there, and is identifying or is telling you that this system is high power PoE capable to do. Let's continue on the low frequency measurements, this delay and delay skew. So as you saw earlier, these four pairs have different twists mean different lengths, and different lengths mean a different delay time when the signal is traveling along the line. And you have to make sure that you're measuring the individual delay time of the signals traveling through the lines here. And you have also to make sure that, first of all, the time itself is not too big. And the second one is that the delta between the four different pairs you have is not too big as well. Because if the delta of the delay time is too different, the delay skew is too big, the receiver on the end side of this link cannot clearly identify the signals coming from the other side, cannot recombine this data word which comprises out of the four different parts you send over the four pairs of data. Okay, so we have to make sure that the delay and delay skew values are kept under certain limits. Okay, this is what the instrument is telling us here. And you see each time when one of these fields in the screen is green, it's within the limits. If it turns to red, you lost the limits. You left the limits, and you have to see what it happened. Okay, this delay measurement we're also using for another parameter. We're using for the length measurement. The length measurements here you can see we're also measuring all the four pairs. What is now the actual length of a cable? What pair are we going to use? The standards are telling us you have to use the shortest pair. So the length information of the shortest pair is the length of a cable. Installers don't like it because they always want the longest pair, but the standards is very clear on this. You have to use the shortest pair as a length statement for the cable itself. Okay, length. What you see maybe is that the length here has no green field and no red field. Why not? Because length is no pass-fail criteria, not in the international or the European standards. It's just a pass-fail criteria in the tire, in the American standards. Okay, if you see here some green field or red field, you know I'm using the wrong standards. Okay, now let's turn to the RF parameters. RF parameters are a bit more complicated because RF parameters are frequency reliant. So what you see now, we don't have only one single limit value, but we have a limit curve. Okay, and we're trying to have our measurements, whatever measurement it is, either below this limit curve or above the limit curve. Okay, and if something is below this limit curve, very nicely below the limit curve, we get this very nice green tick over there. Okay, if our measurements are above the limit lines, we get this ugly red sign here. Okay, but there's also a small band, let's say, surrounding this limit line, and this is where the measurement uncertainty of the instrument is working. And this small band you see here between this thin red and thin green line, when a measurement value is in this small band, you see it gets a little asterisk. Okay, so the instrument is telling me that this value was below the limit line, but it was so close to the limit line that it could be also on the other side. It's within the range of the measurement uncertainty of the instrument. The same for this one here. If we are above the limit line, but we are very close to the limit line, you get also this red X with the asterisk on it. And this tells us you're very, very close to the limit line. Okay, so there are more indicators now we see as just a pass or a fail. And you have to make sure, as an installer has to make sure, before he starts an installation, he has to talk to his customer. And he has to talk with the customer about how are we working with these asterisks. Do we accept the instrument statement, or are we very negative today? And we also do not allow a pass on this one here. Okay, so if the asterisk appears, repeat the measurement, redo the installation, whatever. Okay. There's also a fifth sign we can have on the measurement. This is I for information only. Information only is when you see, for example, measurements jumping over the limit line, but part of the limit line are colored in green. This has to do with some certain formulas which are in the standard, which allow certain parameters to cross the line under certain conditions. And if these conditions are met, we can even cross the limit line without giving us a fail statement. Okay, that has to do with short lengths, with low frequencies, with special behaving when doing measurements on short lengths, and so on. Okay, but it would go too far to explain it too deep on this now. But there are certain rules and certain formulas in the standards we have to interpret in the instrument, and this giving us these different signs here of pass and fail. So now let's start with the actual parameter. The first parameter is insertion loss. Insertion loss, very simple. We are sending some signals, we transmit some signals here down the line, and we look the amplitude at the amplitude on the other side. Okay, where do we lose this information? We lose the information on the line, on the cable itself. So the longer the link is, the less the signal is on the other side. The higher the frequency of the signal is, the less arrives on the other side. This has to do with this low pass characteristic of the data cable, and with the insertion loss behaving of the cable. So when this parameter insertion loss is failing, usually the cable is simply too long, or it's not of the best quality, not of the quality category we need. So this is an example to show you the screen for insertion loss. So you see here, this red line is a limit line, and you see here 4 measurement lines for the 4 pairs. And these 4 measurement lines are like one line. What does this mean? This means that this data cable has fantastic insertion loss performance because all the 4 channels are matching. That's a modern, typical, good quality data cable. Okay, next parameter, RF parameter is next crosstalk. What's happening here? What are testing we here? We are testing here a behaving that's inherent in this data cabling system. So we are transmitting here again a signal on this orange line. The signal is getting lower because of insertion loss effects, but also what we get some electromagnetic fields surrounding now this orange cable pair where the signal travels. And this electromagnetic field is also now working, let's say, on the other 3 pairs in the cable. And what's happening if an electromagnetic field is working on a cable? You get some induction. And these induction effects you get here, this is called the crosstalk effects. Okay, we don't want to have the signal here, but we get it. Okay, and we have to make sure that this signal, which is a noise signal on our other line, is kept low. The cable guys are doing it very nicely. They keep it low because of the twist of their cable. So where nowadays most of the crosstalk or the next is coming from are the components beginning at the end. Okay, because there we have to open up the twist, and we have to guide the signals for a centimeter or two within these connectors nowadays. And at the end of the connector, we have this funny situation that we have these 8 lines, and what we are doing is we are crossing 3, 6, and 4, 5 in the middle. Okay, so it's not as we would like to have these 4 pairs this way, but unfortunately one pair is enclosing the other ones, and this is RF. For our parameters, it's absolutely nightmare. Okay, and we test this for all the 4 pairs, and we get, in the summary, we get 12 measurements, because we have to do these measurements. Let's go back one slide. We have to do these measurements not only from one side to the other side, but also from the other side to the beginning. Okay, so 6 measurements from here, 6 measurements from here. This is why we're using a second instrument on this, combined together in one screen. So you see here the measurement, these 12 measurements here, and here on top, the red one is again the limit line. So this is passing very nicely the limit line. And what we also can do, we can isolate each individual pair we are testing and can have a look at this if we get enough time. RF parameters are often the parameters which are failing mostly. So when we talk to customers, classical telephone calls, I got a next problem, what to do now? First of all, we have to find out where the next problem is coming from. Is it coming from the system itself, or is it coming from the instrument itself? The instrument we can easily isolate. We're doing a reference measurement against our reference link we have at the construction site, or what we sometimes good enough, we just swap the instruments. If we swap the instrument, the faults might wander from one side to the other side, and then we know it's the instrument problem or it's the installation problem. And to support this localization of the problem, we have a functionality called the locator. And the locator here, as you can see, is giving us let's say a distance indication. Where is on my link, where are the next issues, or where are the next problems? Okay, this one is a good one. So we've got one in the beginning of the link and one at the end of the link, one disturbance, again, one next effect. This is simply where the connectors are. But if you get this one like here, where you got a next disturbance somewhere in the cable run itself, you know something is wrong here. So what happened here? Somebody has cut the cable and combined it again with a luster terminal, which is definitely not good enough for an RF transmission line. Okay, that's about next. The next one is ACRN. That's just a calculated parameter, attenuation crosstalk ratio at the near end. This is what we're doing now, is we are calculating now, make a calculation between the next and the insertion loss we just measured. That's just an indication for the cable manufacturers how good the installation is. For us as a test engineers, it's not interesting, this parameter, because it's just a calculated parameter. What else do we have? Return loss. Return loss is very important. Return loss gives you some indication about the reflection you got on one link you have. And where are reflections coming from? From mismatches of the impedance. And usually, where are the sources of mismatches is where you change, for example, the type of cable from a flex cable to a solid cable, where you have connectors in between, plug jacks in between. These are sources for reflections, for disturbing the matching of the resistance of the impedance. Or where it's really bad now is if you have destroyed or mishandled your cable in the installation. So where the cable has not its geometry as it's done by the manufacturer of the cable. So if you stretch a cable, if you put knots in the cable, you get disturbance of the impedance. And if the impedance is not 100 ohms all over the way, you get reflections. And if you do it, if you're cruel to the cable, you get reflections which are very high and which are failing the return loss limits. Here are some pictures from the instrument, how they look on the testing here on the tester. And also on this return loss, we have this locator functionality. So again, this is a good one here. You got a little reflection on the beginning where the first connector is, and you got a little reflection on the end where the second connector is. That's fine. Okay, what do you hear? Here you don't even see almost the first and the last connectors anymore, but you got here somewhere in the middle of the cable, you got two impedance or reflection pulses here, and they are in a distance of about 2 meters. So what happened here? This pure cable was lying on the ground, and a forklift truck was passing over the cable. So you see that's the distance of the two wheels of the forklift, and in this distance of the forklift wheels, we got enormous reflection because the impedance of the cable is broken here. Okay, the cable itself is still connected, but the impedance is not working anymore. Then you got parameters like this one here, ACR minus F, attenuation to crosstalk ratio at the far end. That's a parameter which was introduced with gigabit Ethernet. This parameter is looking into the behaving of signals at the end of the line. So you're sending here in signals, and you see what happens at the end of the line. Because if you use data cable, which is not very nicely constructed, and there's a very big difference in insertion loss on two pairs, it might happen that signals ending up here might create a crosstalk, actually a crosstalk here, which is killing the signal on this side here. Okay, so the receiver can't read that signal anymore. And to make sure that we are not using cables which are different in attenuation, this parameter was defined. It gives us an indication about the quality of the data cable. Okay, so that's the way it looks. It's very nice curves here, very nice measurement lines. General, never take care about these things going here down, these reflection spikes going here down. We always look just to the limit line and to the difference between this line here, this top line here you can put on this, and the difference here in between. Everything that's going down here to lower areas, we don't take care about. So last group of parameters, power sum parameters. What is power sum parameters? Power sum parameters are purely calculated parameters from basic measurement parameters. So therefore we have power sum next, power sum ACR minus N, and power sum ACR minus F. Where does this come from? It has to do with the amount of disturbance we have nowadays in a data cable. If we look back to history, in the old days with 100 megabit Ethernets, we only had 2 pairs of cable. Okay, these 2 pairs, one was the transmitting pair, one was the receiving pair. How did it work? So here a signal was sent out, and the signal created here a next. Okay, and this next was influencing the receiving level here. Okay, and in the old days, we just had to make sure that this crosstalk is lower than the signal which appears here. And then it was fine, and the signal could be read. Same story on the other side. What was disturbed here? The receiver here was disturbed by the transmitter from here. This was good old 100 megabit Ethernets. Nowadays, we are using 4 pairs of data. And what we are doing now is we are dividing our signal we want to transmit in 4 pairs. And the 4 pairs are shifted on the other side to the other side with 1 clock. Okay, with 1 clock pulse. Who is now disturbing my little receiver here? In general, we have at the same time 4 receivers here and 4 transmitters, and the same on the other side. It's full duplex communication. So who is disturbing who? So now let's have a look to our little receiver from earlier. So this is the receiver, and he still got disturbed from this line here, but now also he got disturbed from crosstalk from the other 2 lines, which are also under signal today. Okay. The same for the other side. The other receiver here is disturbed now from the other 3 pairs. So we got now more disturbers. We got 2 more disturbers near on each side. This is the only ones? No, because we have full duplex signaling. Also, the other 3 lines here are sending signals down the line to me here. Okay, and what's happening here? Here is a kind of fixed happening. This one, far end crosstalk. So instead of 1 disturbance we had earlier, now we have 6 disturbers for every receiver here. And the quality of the receiver has to be as good to find the signals here and to analyze or isolate the good signal here from the noise floor. And if you look to the other side, now we got 6 disturbers there as well. Guess what's happening if I would now draw all these red lines in for all my receivers here and receivers over there? You wouldn't see anything again from the lines in the background. So nowadays we are flooding the data cable on gigabit Ethernet with all this amount of noise and the crosstalk. Okay, so we have to make sure to use high quality cables and to do good installations. Okay, summary of these test standard, of the test parameter here. Usually I recommend to print out this page to my installers and take it to the instrument. And if you're on site and you got one of these exotic faults, you can have always a reference on this sheet to have a starting point for your investigation on a fault. Okay, let's go to the last topic. We're a little bit behind time, so let's talk about the wire expert. It's a very quick talk. So here's the wire expert. This is the instrument doing all these fantastic certifications. It's a system comprising of two identical instruments which can be switched to a local remote as you want to have it, or you can have two individual locals or two remotes if you work together with other systems and so on. And you can use it for all kinds of applications where you find Ethernet. So classically we have this premise wiring, as we were talking about, in the different levels, categories. We also can touch patch cord, as you have seen on the NPTEL testing. We have patch cord testing adapters. And what we didn't mention is we also have coaxial adapters, so you can test coaxial cables as well. Then we have backbone testing, as we call it. This is the world of fiber optic testing. We're going to talk tomorrow about this. With the proper fiber optic adapters, you can do testing of single mode backbone, and you can test multi-mode distribution as well. We also have an approach we call data center. Data center is going up now to this Cat8 area. The Cat8 area going up to 2000 megahertz, and there we have special testing adapters, measurement adapters for the different interfaces which are used in the Cat8 world, like the Terra, the GG45, and of course the RJ45 going up to this world. Industrial, as you can see here, we also have a complete suitcase full of adapters and special test codes for the whole industrial world to cover all the different connector interfaces with the proper measurement equipment. And last but not least, we also have people using the instrument in laboratory as a supporting tool for a network analyzer, supporting doing quick measurements. This is a special application and dedicated laboratory use. What actually do we want out of a certification? At the end of the day, it's reporting. Here are some samples of reports we are using or we're getting out of the instrument. Here, this is the classical report for a certification run on a installation link. Here is a summary page, which you put on top of the other individual pages in a complete documentation, sample of coax measurement, sample of fiber optic, we will see tomorrow in detail, plus fiber optic, fiber end phase inspection, but that's, as I said, topic of tomorrow. So that's it from the topical, from the technical side of today. Quick outlook to tomorrow. Tomorrow we're going to talk about about fiber optic measurement in depth, deeper as we did last week. And on Thursday, it's, as I said earlier, it's active Ethernet, basics of active testing, which was the fourth group of test and measurement as we had. Okay, that's it from me. A little bit overtime, so thank you very much for your attention. Now I'm looking to Alex. Alex, to the stage. Let's talk about questions, if somebody raised questions.
First, thank you very much for the very interesting webinar with a lot of details, standards, DCRU, all the things. I think it was really understandable. So no questions today.
Oh, really? Oh,
so this was a perfect webinar with all the details on this.
Okay, so fun.
So we had a lot of attendees, but no questions today. That's good.
If you got questions later on, here's our contact address and my contact address. Feel free to get in contact with us every time you want. And yeah, if no questions are,
thank you very much
for listening, and we will leave the stage and see you tomorrow.
Bye-bye.
Bye-bye.